Let's continue our discussion talking about torque on a current loop, looking at motors and meters. So they're very similar. So I'm going to focus on motors. So motors is a very common application of magnetic force on a current carrying wire. Um, they have loops of wire and a magnetic field. And when current passes through the loops, the magnetic field exerts some torque on the loops, which rotates some shaft, and the electrical energy is converted into mechanical work. So this is the basic idea of motors. So we can look at this here. And so we have a magnet on either side, the north and south pole, and we have a loop of wire here with some current flowing through it. As you can see, it's in this direction, okay? So it's in this direction. So it goes all the way through here and back down. Okay, so this is the loop. And with that current and magnetic field, there is some torque that is associated with it. And so the system here starts to move. And it moves with some torque T, or tau, sorry, um, around here. And that's due to the forces involved. So there's a magnetic force that gets introduced due to the magnetic field and the current. As we've said before, it is going to be the right-hand rule that we figure out which way it's moving. So it is going to be moving in this direction on this side, since the current is going towards like positive y, we can say. And on this side, it's going towards the negative y, so we'll have a force in this direction, kind of like towards us, okay? So with those forces creates some sort of torque, and so the loop will rotate. The motor will start to rotate. So we have another view of this. So this is like a side view. This is a top view of this system that's happening. So we have a current that's coming towards us now, or out of the page here, where we have that dot. And on this side, we have the magnetic field is going to the, let's say this is the positive X direction. And so the other, when we do our right-hand rule, remember our thumb will point in the direction of the, point in the direction, yeah, point in the direction of the current. So coming out of the page, so you can even do this with your hand, coming out of the page, and then our B field will be pointed this way towards the X direction. And so our force will be going here in like the positive Y direction. So hopefully you can see my hand doing that, but if not, we can look at this in class as well. So this tells us that we have some magnetic force going in this, say, positive Y direction, okay? On the other side here, where the rest of the current is flowing, we have the current is going into this page, or into the screen here. So we will do the same thing. We have our thumb in that direction. We have our magnetic field in the positive X direction. So our palm will be pointing downward towards the negative Y direction. So this is now F, negative Y direction, okay? So with those two forces, we start to create a torque involved. So with this torque, we can give a direction to it. It's kind of like if you spin something, right? It's the same exact idea, but this is now with magnetism, okay? So this will create a torque. So the torque on a current carrying loop, which we have here, In a uniform magnetic field, which is what we have a magnetic field flowing through that wire, that current carrying loop, sorry, not wire, the loop. We have tau is equal to W, the width, should say width, I, the current, and L, the length, B, the magnetic field strength, sine theta, where theta is that angle that we see here, which is the angle between the current, let's see, the current wire, yeah, the wire where the current is with respect to the middle there where the torque would be happening, and the force. So it would be between the torque, sorry, I'm trying to put this into words, but it's very visual. The current wire is here, flowing out of the page, and this is connected by a wire to this middle part here, this shaft where the torque is introduced. And so that angle between, that and the force is going to be our theta, if that made some sense. I'm going to go ahead and rewrite this. So we have W, nope, that's going to be bad too. W is the width, L is the length, I we know is the current, B we know is the magnetic field strength. And so with that information, we can also have where we have a situation where we have like a solenoid instead of just one wire. So we can have, I'm sorry, not just one wire, one loop. So we can have multiple loops like this, okay? And so with that, we have another equation, tau is equal to N, or the number of turns, times IAB sine theta, where A is the area, W times L. So it's a very similar equation, but now we have, we account for the number of turns, okay, in the loop. Or I'm sorry, in the solenoid, say, okay? So this would be like if we had a solenoid, okay? And in this, we can say that the net force on the loop is 0, since it will be in equilibrium. Okay. And here's a quick note about the units. Here on tau, that is Newton meter, or a meter squared times Tesla. Okay. Where A is our amperes. Remember, that's amperes. Okay. All right. So let's go ahead and put this to use. This example says find the maximum torque on a 100 turn square loop, hint square, of a wire that is 10 centimeters on a side that carries a 15 amp of current in a 2 Tesla field. So let's start labeling things. 100 turn, that tells me my N. The fact that it's square tells me that I can find the area is equal to length squared, right? A wire, this is going to be the length that carries this current I with this B field. Okay, so our torque, remember, is N times IAB, right? IAB sine theta. And if it doesn't tell you some sort of angle, then we can probably safely assume that the theta is 90 degrees. So Theta is 90 degrees. That may not be a great assumption every time, but it's also a square loop of wire. So we have something like, if I can draw this, oh boy, don't look at that. Who put me in charge of drawing? Okay, let's pretend that's a square. Okay, so we have some current flowing through it like that. And this is going to be a square, so this is L, and this is also L, the length. But it has 100 turns, so times 100 of those. And carries some current with some B field. Okay, so let's go ahead and plug these values in. We know N is equal to 100. And note that N does not have a unit because we are just counting the number of turns. So we can just say it's 100. Okay, no units on that guy. Current is 15 amps. The area is going to be L squared, so it will be 10 centimeters or 0.10 meters. So 0.10 meters, that's going to be squared to find that area piece. And then our magnetic field B is 2 Tesla. Okay, so we can throw that into a calculator. 100, actually I'll do 0.1 times 0.1 first, times 100 times 15 times 2, and we get 30, and torque is in Newton meter. We just remembered that guy. And that will be our torque of this current in a solenoid. So this is the torque going on here in this motor. Okay. All right, so let's go ahead and continue talking about the magnetic field created by a long, straight current carrying wire. So this, we have a current just in one direction on a wire. Okay, so we're not worried about loops yet, just talking about the current in one direction on a straight wire. Okay, so it was found by experiment to be equal to mu naught times I, the current, divided by 2 pi times r, that distance. So I is the current, r is the shortest distance to the wire, and mu naught is some constant called the permeability of free space, and it is given by 4 pi times 10 to the negative 7th Tesla meter divided by ampere. Okay, so to figure out, like I said before, we were going to talk about this, the another right-hand rule, and this is to find the direction of the magnetic field when we have some sort of current carrying wire. Okay, so we're not looking at electrons or protons in free space. We are now looking at a current carrying wire. Okay, so what we do is we point our thumb in the direction of the current. So it'll be in, in this case, it would be in the positive y direction. And the fingers, your fingers will curl in the direction of the magnetic field. Okay, so here I have my fingers curling in towards me, and so I have a magnetic field that's pointing towards me, and it'll go all the way around. So that tells me that I have a B field that's going around like this, okay, around that wire. Versus if I have a current, say I have a current flowing in a wire in this direction, I'll do the same thing where I have my thumb pointing in the direction of the current, and I curl my fingers and it'll go around the wire in the opposite direction. So I'll have a B field that's in this direction now. That's a terrible arrow, but you get the point. Okay? All right, so let's look at a quick example of this. Find the current in a long straight wire that would produce a magnetic field twice the strength of Earth's at a distance of 5 centimeters from the wire. The magnetic field of Earth is about 5 times 10 to the negative fifth Teslas. So we have our B field due to Earth. Whoops, I did not mean to write it like that. I meant to put Earth. And we have 2 times that amount. This is our R, or we can put it into meters. That's what we'll need it in. Okay, so let's go back. This is our equation. So B is equal to mu naught, oops, times I divided by 2 pi R. Okay, so we are trying to find the current. So let's go ahead and rearrange this. So we have I is equal to 2 pi R times B divided by mu naught. Okay, B we should put is equal to 2 times this amount, so it would be 10.0 times 10 to the negative fifth. Okay, so we want to plug everything in. Our current is equal to 2 pi times our R. Our distance is 0.05 meters times B, or 10 times 10 to the negative fifth Tesla, divided by mu naught, which was, I think, 4 pi times 10 to the negative seventh, I want to say. Yes, Tesla meter per amp. Okay, so we can plug this straight into our calculator, or we can try to kind of simplify it. So we have pi here, we have a 2 and a 4, so that brings that down to 2. And then, let's see, go from there. Come on. Calculator. So we've got negative 10 to the negative 5 divided by okay, so that would be 100, right? And then times 0.05 times 10 divided by 2, and we get 25, and this should be in amperes, and we can double check. Our Teslas will cross out, our meters cross out, this will come to the top, and perfect. So this is our current in that long straight wire producing some magnetic field. Okay. All right, so this is another, just understand the statement. This is a formal statement of the direction and magnitude of a field due to each segment. So each segment of current produces a magnetic field like that of a long straight wire, and the total field of any shape current is the vector sum of the fields due to each segment. This is called the Savart Law or Ampere's law. Okay, so this is just kind of like a hey, know this, but I'm not too worried about it. It is more just to kind of get you guys into the idea that these are laws and I'm not just kind of making these things up while I go along. Okay, so we talked about magnetic fields produced by current carrying wire, a long straight wire, but we can also look at it in a circular loop and a solenoid. So a circular loop is going to be just what it sounds like, what we were looking at before with the torque with motors. So we have a current going along a loop of wire, And that magnetic field strength is going to be equal to mu naught times I divided by 2 times R, where R is the radius of this loop. Okay, so R would be some radius. Whoops, that is ugly. Let me fix that. So in this picture, we can see the person is just confirming the direction of the magnetic field along this wire. And from his, or their, sorry, from their depiction here, we can find the magnetic field. So the magnetic field curls in the, say, that's like the positive y direction. So we can draw that as well. Okay. So this is what the magnetic field would look like with this current carrying loop of wire. And the magnetic field would look like so. Okay, if the current was traveling in the opposite direction, the arrows would just be pointing in the opposite direction. Okay, because the B field would be going in the opposite direction. And then we have the magnetic field produced by a current carrying solenoid. So again, a solenoid is going to be a coil of wire with many turns and loops. So you can see that here. And there is some magnetic field strength that is inside the solenoid. So this is going to be equal to mu naught times N times I, where N is the number of loops per unit length of the solenoid, or N is equal to capital N, which we saw before, number of loops, divided by L, the length of the solenoid. Okay, so in this case, we have a battery hooked up to a wire, a solenoid. So we have the current that's flowing, and it'll continue to flow in this direction, again, kind of like this, right? And so when we put our thumb in the direction of the current, okay, we will see that we have the B field and it's going straight through that solenoid. So this is like a cross-section view of this. So if we cut that in half and look inside, this is what we would see. So we'd see our magnetic field B here, okay, and these would be, wait. No. This is our, how is this depicted? Sorry, give me just a second. We've got in and out. Okay. This is our magnetic field. So we cut it in half. This is going into, out of, into, out of. Yeah. Sorry, this image is a little bit confusing. So this to me is the magnetic field here. And I'm trying to figure out what the red is then. I think it's also magnetic field, but just at a different, because these are closed loops, I'm thinking that's what it is. But it's just kind of an interesting depiction here. So we have our current here, right, going into the page and then out of the page. Oops. On either side. So these are our wires, and or the loop of wire. So this goes out of the page and then into the page. So out of the page, we'd have the current going this way, and our magnetic field will curl around. Yeah. Okay. So this makes sense. This is all the magnetic field here, the red and the blue, but it's just that some of them will actually connect to a loop, and these will not. They're kind of off to wherever in space, okay? So this is a depiction of this again. So we have the magnetic field flowing through, straight through the solenoid, okay? So let's look at a quick example of this. So it asks, what is the field inside a 2-meter long solenoid that has 2,000 loops and carries a 1,600 amp current? So we're looking at solenoids. So that's going to be B is equal to mu naught in I. B is equal to mu naught in I. And N is equal to the number of loops divided by the length. So we have the length here, we have the number of loops, and we have the current. So we can say is the N, small n, is equal to 2,000 divided by 2 meters. Okay, so that's going to be equal to 1,000 per meter. That's the units. So then we have mu naught, which was 4 pi times 10 to the negative 7th. I don't remember the units on that guy, so I'm going to go back. Tesla meter per amp. Okay. Tesla meter per amp times N, which is 1,000 per meter, and our current, which is 1,600 amps. Okay, so let's do this. So we have 4 pi, 4 times pi times 10 to the negative 7th times 1,000 times 1,600. So we have a B field of approximately 2.01, and that is in Teslas. So about 2 Teslas is the magnetic field strength. Remember, this is magnetic field strength. Okay. All right. So that's all we have for this section. I know it was probably a lot to take in. I know it is. So we will do some, have some more examples on the homework. Feel free to ask questions. Please ask questions. And we can even look at it during lab time. Okay. So next time we're going to start to talk about electromagnetic induction and then go from there. All right. Thanks.